Welcome to the next lecture in our course on mechanical operations. In the last class we started discussing top-down methods of sonoparticle or nanoparticle synthesis, and the two methods that we talked about are ball milling and high energy ball milling, which is a variant of that, and cavitational size reduction, also called sonofragmentation, which uses an acoustic field and cavitation energy to break down micron sized particles into nano sizes and create nanoparticles. Now the challenge in all these processes is scale up. It's very easy to make nanoparticles, a few milligrams at a time in a test tube, but in order for commercialization you need to be able to make these particles in much larger quantities, and that's called scale up. So when you talk about scale up in particular, the ball milling really doesn't lend itself to that, because as we saw in the last lecture, to produce nanoparticles by ball milling takes a long time. It can take 20 hours, and it's basically a batch process, and the particles come out of the ball mill in a highly agglomerated state, so you need a separate step to de-agglomerate the particles and so on. So that's pretty challenging. Well, I guess we are back on. So on the other hand, the acoustic process actually lends itself to scale up, because it can be operated in semi-conductor continuous mode as well as continuous mode. In the semi-continuous mode, what you can do is you can have a tank that you fill with a liquid, couple it to an acoustic field and set up a cavitation system, and you can have a container containing particles to be size reduced, stick it inside this ultrasonic tank, turn on the ultrasonics, and size reduction will happen because of cavitation. You can do this using either a tank type sonicator or a probe type sonicator, as we mentioned last time. And what you will see is that stratification will happen. Again, we discussed this briefly in the last lecture. The nano sized particles will naturally float to the top, and the micron sized particles will stay at the bottom. So you could conceivably have a system where you are continuously draining out the top layer, which will be enriched in the nanoparticles, and the bottom layer will contain the particles that are not yet size reduced. So periodically you can go and recharge the system. So it's kind of a semi-continuous process in the sense that it is a batch process, but you can do a batch every 30 minutes or so, where you take out the two layers separately and collect the nano sized particles in your container for subsequent processing. Now in a continuous system, what happens is that you set up a recycle process. So the bottom that contains the large particles, you can conceive of recycling it so that these larger particles get taken back through the size reduction system. And alright, so in a continuous process, what you do is you have again a system with suspension and particles, and you sonicate this. The large particles are at the bottom, and you continuously recycle to the top. The finer particles you continuously drain out, right. So you can imagine doing this as a continuous process, and the nanoparticles will be taken out through this discharge, and the coarser particles will keep getting recycled. So this is a fairly simple concept which takes advantage of the fact that sedimentation causes an automatic separation by size, and so it's easy to conceive of continuously recycling the coarse particles for subsequent size reduction. Now there are commercial systems available for doing this. At lab scale, you can conceive of a simple beaker system with an ultrasonic probe that sticks in. So you put your particles in there and you turn on the ultrasonics, and fine particles will continue to be generated. You can scale this up to a pilot scale, basically larger size. The chamber volume that contains a particle suspension to be size reduced is now larger in size, so you can put more quantity of matter through this system. And finally, you have an industrial scale ultrasonic disperser. There is a company called Hilscher in Germany that makes these systems, and the industrial scale ultrasonic system has what is known as a flow cell. So, the way that works is you can use it in two modes, a single pass mode and again a continuous mode. So, you have an ultrasonic generator, ultrasonic transducer. The flow cell is where the size reduction happens. So, the particles to be size reduced are kept in this tank that continuously cycle through the flow cell. Size reduction happens and then they are taken into a second tank where the fine particles are collected. Okay. This is what we call a single pass system. So, what you get in this tank is actually going to be a mixture of size reduced particles and particles that have not yet been size reduced, because any size reduction process, whether it is in a ball mill or in a sonicator, is never 100%. Some fraction of the particle population will get size reduced, but some fraction of the particle population, just due to statistics, will remain in its original size. A variant on this is a continuous recirculation loop, which takes this concept that I have sketched and makes it into a commercial system, where again you have the ultrasonic generator, the ultrasonic transducer, flow cell, but it is a single tank. So, the same tank contains the feed material and as well as the product material, and you are continuously feeding coarse particles into this, and you continuously recycle this through the flow cell where size reduction happens, and you kind of keep doing this until you reach the size distribution that you want. You can be continuously feeding into this tank as well, so that the product is continuously getting mixed with the new feed, or you can again run this in semi-continuous mode where you take in a certain amount of feed, do this recirculation process for a fixed period of time until you are sure that all the particles have been size reduced to a certain range, and then you take out that batch and put in a fresh batch and do this over again. Alright, so what we have talked about so far is synthesis of nanoparticles. How do you either grow nanoparticles from small dimensions, or how do you size reduce from larger dimensions to make nanoparticles? What we are going to talk about now is another process that is quite important in making product using nanoparticles. Nanoparticles are just building blocks. A nanoparticle by itself is useless. You have to put it to some kind of use, and one use is to make composite materials. If you take a basic polymer and disperse nanoparticles into it, its properties change dramatically, and you can get tremendous enhancements in the functionality of the polymer. So, nanoparticle dispersion is another important mechanical operation, and so let us talk about nanoparticles in suspension. We have reviewed this earlier in this course. Nanoparticles in suspension have a cohesive tendency. The hydrophobicity versus hydrophilicity is one of the factors. So, the particle suspension is very dynamic in nature. It does not stay static. Particles agglomerate, mean size increases, number of particles decreases, and in order to kind of model this behavior, you need something called a population balance model, which looks at both birth and death of particles in a certain size range. So, there are fairly detailed population balance models that have been derived to simulate what happens in a size reduction system, but it is still a matter of fact that no matter what you do, you can put surfactants in, you can use charge dispersion and so on to try and keep nanoparticles apart, but they will agglomerate to some extent. So, if you are going to be using these nanoparticles subsequently in another step of the process, you have to do a dispersion step just prior to further processing. For example, if you are going to take these nanoparticles and mix them into a polymer to make a composite, you have to do a dispersion of the nanoparticles just before you introduce this into the polymer. So, when you do that, just like particles in a suspension agglomerate, when you inject particles into a polymer, again there are issues about non-uniformity of the dispersion and also the distribution of particles in this nanocomposite. When you inject nanoparticles into a polymer to make a composite, what you are relying on is the fact that the nanoparticles are well dispersed in the composite. But if they start agglomerating in a composite, they start to form what are called bridges. In the worst case, you can imagine that if you have a polymer and you have nanoparticles that are dispersed in this, if agglomeration starts to happen to a significant extent, you can almost form a continuous line or layer of nanoparticles, which then defeats the whole purpose because it does not have that nano property anymore. Up to a certain amount of agglomeration it has micron properties, and after that it has millimeter properties, and after that it has virtually no effect. So, you want to prevent this so called bridging of nanoparticles from happening. Also, when this kind of bridging starts to happen, you need to put in more nanoparticles in order to get the desired effect. So, the filler volume increases, which means there is increased cost, right. So, just as you want to prevent agglomeration of nanoparticles in suspension form, it is also important to prevent agglomeration of nanoparticles when you have dispersed it into a solid composite material. So, we have looked at cohesive force earlier in this course, and there is actually a dependence. If you plot all the different forces that we listed earlier and you plot the total of cohesive force as a function of distance of separation between two particles, this is the kind of curve that you will get. There are two peaks. There is one when the distance of separation is very small, and there is another peak that happens when the separation distance is a little longer, but eventually the force decreases to an asymptotic value which is very low, close to 0, and it never reaches 0 because, at least according to some quantum theory, there is always an interaction between matter no matter how far away they are. But in general, you can take this kind of behavior to happen in a suspension of nanoparticles. So, we have seen this before, that for a population of particles, the number of particles at any time t can be related to the number of particles at time 0 through this formula, which involves Boltzmann constant, temperature, time, the Stokes-Cunningham slip correction factor, and viscosity. So, agglomeration is accelerated by higher temperature, longer time, lower viscosity, and smaller size, right. We have seen this earlier in one of the lectures. And again, you may recall that cohesive forces are of basically 5 types: the van der Waals forces and electrostatic forces, which are common to cohesion as well as adhesion, and then in addition we have the capillary force, the viscous force, and the spring force or contact force. And again, the capillary force is the sum of surface tension and pressure. The viscous force is a sum of the normal viscous force and the tangential viscous force. So, this should all be in your notes. And of course, the spring force or contact force is a function of, is a sum of the normal and tangential components. So, what does this all contribute to? Now, this is a very key diagram in the manufacture of nanocomposite materials. What you look for, let us say that basically what we are looking at here is the polymer matrix itself, and obviously these are the nanoparticles that you have injected. The behavior that you want is this quadrant. You want the particles to be well distributed and well dispersed. Now, these mean different things. This is poor distribution and this is good distribution. And in terms of dispersion, this is poor dispersion and this is good dispersion. What do we mean by the two? Dispersion refers to the lack of agglomerate formation. So, when you have nanoparticles that are well dispersed in a composite, or in a suspension, what we mean is that they are not clustered. You can identify the presence of individual nanoparticles. Distribution, on the other hand, refers to the spatial uniformity of how these particles are distributed in a suspension or in a composite. So, when you look at something like this quadrant, this represents good dispersion because the individual nanoparticles can be clearly seen, but it is not a good distribution because the particles are clustered together in different regions of the composite material. And similarly here, this is actually good distribution because you can see that even though the particles are clustered together, they are well distributed in the polymer matrix. However, it has poor dispersion. So, all these three quadrants are not optimal. They are not going to give you the nano functional performance that you are looking for. What you need is this, which represents both good distribution as well as good dispersion. So, the challenge in any nano processing, particularly when you are trying to make a nano composite material, is to achieve this D quadrant. So, how do you do that? Again, this is primarily a mechanical process or mechanical operation. The three ways in which you disperse nanoparticles into a composite: just simple stirring. This could be using a physical stirring mechanism or a magnetic stirrer; shaking, where you put it on an orbital table and use an eccentric motion of this shaker table in order to get good mixing. The third is, again, just like we use sonication to do size reduction and synthesize nanoparticles, you can use sonication again to do this distribution and dispersion of the nanoparticles in the composite. There are other processes that are used for dispersion. A supercritical fluid is one that has some of the properties of a liquid and some of the properties of a solid. It's a good medium for dispersing nanoparticles because it has low viscosity. So, a nanoparticle that is immersed in a supercritical fluid can be dispersed much more effectively than nanoparticles that are dispersed in a highly viscous medium. So, you can suspend the nanoparticles in a supercritical fluid and also do the blending process of particles into the polymer using supercritical fluid as a carrier, and that improves your effectiveness of dispersion. Magnetic media can be used, particularly if the particles that you are using as fillers have magnetic particles. You can use a magnetic field to do good dispersion of these particles. And similarly, you can set up a charge field and use the charge distribution on the nanoparticles as a way of dispersing the nanoparticles. Sputtering is another technique. You can use high energy impact of a surface by ions in order to make nanoparticles that again have a tendency to disperse well because of the charge that they carry. Spray drying is a process that again induces charge on the particle, and the charge is such that it causes repulsion between the particles. So, when you combine spray drying of a suspension with sonication and the use of a dispersant, you can get a well dispersed system of nanoparticles in a polymer composite. Another method that is used is simply impaction of aerosols. So, you prepare these nanoparticles, use an aerosol generator to make little droplets of these nanoparticles and physically impact the polymer with this suspension, so that you use the kinetic energy of the suspension of aerosols to incorporate these nanoparticles at the location of impact. So, it is a line of sight process. You are you can imagine, so almost like shooting with a gun, a suspension of nanoparticles at a polymer. So, the nanoparticle sticks to where it hits the composite. So, this is another way where you can get good separation of nanoparticles in a polymer composite. By the way, one thing you should remember is when particles are suspended in a liquid, they can easily move around. Their mobility is very high. but when the particles are located inside a solid matrix like a polymer, they cannot move around that easily, because obviously the viscosity of any solid is much greater than the viscosity of any liquid or gas. So once you have incorporated the particles into the matrix, they do not move around much. The stratification or poor dispersion / poor distribution happens prior to incorporation into the matrix. And finally, ultrasonic dispersion. As we have seen before, when you couple a suspension to an ultrasonic field, it has two effects. One is the cavitation effect, which creates nanoparticles by fragmentation. The other is the so called acoustic streaming effect, which imparts a very high velocity to the particles. And you can imagine that, just like in the previous case, if you can make the particles behave in a highly dynamic fashion, they are more likely to be uniformly distributed than if they are static. So in ultrasonic dispersion, you use a combination of cavitation and streaming to get a good distribution of nanoparticles into the polymer matrix. So there are many examples in literature of where sonication has been done to disperse nanoparticles into composites. This is a system that is used to take zinc oxide nanoparticles, and using a two-step dispersion process with sonication as the mechanism, you can incorporate it very uniformly into a polymer matrix. There are other literature citations. People have done polymer clay nanocomposites using ultrasonically assisted polymerization as well as mixing. The ultrasonic treatment has been used to make aluminum based composite materials. So use of sonication as a method for producing nanocomposites is fairly well reported in literature, and we have done some work in our laboratory also to do high frequency blending, or we call it sono blending of particles in suspension. Here is some data from our laboratory. When you do this process of sonication, you get this separation where you form two layers, right? One layer has larger particles and one layer has finer particles. And if your purpose is to blend these particles very effectively and make a uniform mixture, one simple way to assess the uniformity is by comparing the size distribution of particles here to the size distribution of particles here. In a well dispersed solution, there should not be any segregation. The size distribution in this part of the suspension should be equal to the size dispersion in this part. So if you plot that as a function of, for example, ultrasonic frequency, you can see in this chart that level 1 is basically the top portion, which contains the fine particles, and level 2 is the bottom portion that contains the large particles. What we are plotting here is turbidity. If you remember, turbidity is a measure of particle size distribution in a suspension. So the point is, as long as these two bars are very, very different, that means it's a poorly dispersed solution. The closer these bars are to each other, the better dispersed the solution is. So if you look at this graph where you have done sono fragmentation at 20 kilohertz and then you have done the dispersion at 58 kilohertz, you can see that the turbidity for the two layers is now much closer together. You have virtually achieved the uniform dispersion characteristic that you are looking for, and you can see that there is a dependence on time as well, and you can do this blending at different frequencies. So the previous slide we showed what happens when you use 58 kilohertz as your blending frequency. This chart shows what happens when you use 132 kilohertz as a blending frequency. So the key thing to note is that at 58 kilohertz it takes you almost some 30 to 60 minutes to do the full blending, whereas in the case of 132 kilohertz you can get it done within 15 to 30 minutes. So this suggests that going to higher ultrasonic frequencies gives you better dispersion efficiency. So if you can actually plot this, you can plot ultrasonic frequency on the x-axis versus optimum sono blending time on the y-axis, and you can see that 58 and 132 kilohertz frequencies give you much better dispersion characteristics compared to 33 kilohertz, which is a low frequency system. So basically the implication here is that for synthesis of nanoparticles, low frequency is good because cavitation is very intense, but for making a very uniform blend in suspension form or for making a very uniform composite, higher frequencies are better because cavitation is not very strong, but acoustic streaming kicks in, and that provides a very uniform distribution of nanoparticles either in suspension form or in the composite form. And this is again more data for different particles. Basically what it suggests is that clearly the combination of 58 kilohertz for synthesis and 132 kilohertz for blending gives us the best results that we are looking for. Just another way of plotting the data, which again reinforces the same conclusion. And so let us skip this. So when you form a composite using nanoparticles, you have to have some metrics that relate to what are the functional enhancements that you have achieved. One of the things that we achieve by using nanomaterials as reinforcement is erosion resistance. Polymers that can be easily eroded in the absence of a filler material can be made much more resistant to erosion by adding nanoparticles as fillers. So in this case there is some data that shows polymethyl methacrylate, which is a polymer with and without nano filler material, and you can see that when you without the nanoparticles the turbidity level is high, which is indicative of high erosion, whereas if you add the nanoparticles you can achieve a much lower asymptote behavior, which indicates low erosion. So this is some data that shows based on functional property measurement that addition of nanoparticle into a polymer improves its erosion resistance characteristics. And this is another way of looking at the data based on mass loss. The previous data was based on turbidity, this is based on mass loss, and again clearly with inserted nanoparticles you get much less mass loss of the material due to erosion. And this is just some data that we collected in our lab of the size distribution of these alumina particles that are incorporated into the polymer, and some SEM pictures. So how do you assess the uniformity of dispersion of nanoparticles in a polymer? It's very difficult to do it quantitatively. So the process that we came up with is a semi-quantitative process. These SEM pictures give you some indication of how the particles are distributed inside the polymer. Can you take these pictures and turn them into a quantitative metric? So the way that we do this is from the SEM picture you select some 50 areas randomly, examine those areas using microscopy. It could be optical, it could be SEM, TEM, depending on the magnification you need. And in each of these 50 areas you count the number of the nanoparticles that you see. From this you calculate the mean of the nanoparticles per sample, and you also calculate the standard deviation. If the standard deviation is less than 10% of the mean, we take the dispersion to be adequately uniform. In other words, the variability coefficient, which is the ratio of standard deviation to mean, should always be less than 0.1. As long as you can achieve that, you have an extremely uniform distribution of particles in the polymer matrix. So again, if you take this particular metric and look at it for various processes for dispersion, you can see that if you simply do mechanical mixing either through stirring or orbital shaking, the ratio, the dispersion coefficient you can achieve is never better than 0.6, which is pretty high. I mean, it basically says your variability is almost as large as your mean. Your standard deviation is almost as high as your mean value. That is not good. Whereas if you go to some of these ultrasonic systems, you can achieve much better dispersion coefficients, and in fact this combination of dual frequency which incorporates elements of cavitation as well as acoustic streaming gives you a dispersion coefficient that is better than 0.1. So again it is an indicator that acoustic processes are much superior to other types of physical processes for achieving both nanoparticle synthesis as well as nanoparticle dispersion. And here is some more functional data. Again you can take a polystyrene nano alumina composite and look at impact strength as a function of filler content. This is a polystyrene nano alumina composite. You can see that there is a clear peak in the value at about 0.4 weight percent filler loading. So this gives you an indication that yes, addition of nanoparticles has an effect on the functional properties of the polymer, and you can actually optimize it by looking at functional property enhancement as a function of filler volume. You can try and locate an optimal filler volume because it is non-monotonic. You cannot keep adding filler. Eventually the filler material will start agglomerating and you will start to lose the effectiveness of the nano additives. So there is usually an optimum percentage of filler which gives you the best functional property enhancement while minimizing the cost. And you can see that in a lot of these systems the concentration of the filler material has an effect, but also the blending process. You know, the process by which you disperse the nanoparticles into the polymer also has a huge influence, and it turns out that this high low dual frequency setting gives you the clearest enhancement in the functional properties. The fact that you are getting such a high peak for one particular filler content and for a particular ultrasonic setting is very encouraging, because it says it is making a clear and distinct impact on the functionality of the material. So you know, this whole mechanical operation of nanoparticle synthesis and nanoparticle dispersion using an acoustic field is a very promising and challenging field, but there are certain challenges that you need to overcome. The first is what we call polydispersity. You know, not all particles that you feed in are of the same size, and any process that you use depends on how spread out the feed particle distribution is. So if you start with a very tight size distribution of the feeder particles, then you can achieve much better functional results. But if the distribution broadens, then the effectiveness of the nanoparticles will decrease. Keeping the micron sized and submicron sized particles during fragmentation is a challenge, and you know, techniques like this have to be employed, but also they have to be optimized to make sure that there is no contamination of your nanoparticles with larger particles, and vice versa. You do not want to lose your nanoparticles with the larger particles, because you know, it costs money. So you do not really want to lose nanoparticles once you have produced them. Dispersion is always a challenge, and dispersion in the suspension form and dispersion in the polymer composite form are both challenges to be overcome. And finally, the incorporation of the submicron particles into the polymer matrix. You have to make sure that the adhesion of the nanoparticles to the polymer is very good, but at the same time you do not want cohesion between the nanoparticles themselves. So it is kind of a dual challenge. In one case you are trying to maximize adhesion, but in the other but you are simultaneously trying to prevent cohesion from happening. So, but these are, you know, challenges that are not that difficult to overcome, and that is why we can use our chemical engineering expertise. So to summarize sono synthesis and processing, sono fragmentation is an effective method to get very spherical particles in the 1 to 300 nanometer size range. Sono blending is a very effective method to prepare well mixed blends of finer and coarser particles, and sono dispersion is an effective method to get good distribution of the nanoparticles in the polymer composite. The challenge in sono processing is to produce sub 100 nanometer particles consistently. Getting down to 100 nanometers is easy, but to make particles that are in the 1 to 100 nanometer size range requires more investigation and work. but the most positive aspect of this process is that scale up is not an issue. You can make tons per day. In fact, that commercial system that I showed you earlier is currently capable of producing about 100 tons per day of nanomaterials. All right, so let us stop at that point. Any questions? Okay, I will see you in the next class.